Hi, everybody. I'd like to introduce a paper that I wrote with Robert Platt at McGill University and Jake Larkin at the McGee Women's Research Institute here in Pittsburgh that will be published in the upcoming March issue of the journal Epidemiology. So in this paper, we looked at ways to address a problem that's commonly encountered in perinatal epidemiology, which is the absence of any data on fetal weight in population-based cohorts. So adequate growth from conception to early childhood is central to optimal health and survival. As such, perinatal epidemiologists are particularly interested in quantifying the specific relationships between fetal weight and the risks of adverse birth and health outcomes. However, because it's typically not measured in population-based cohorts, birth weight is often used as a proxy for fetal weight. Unfortunately, this practice has been shown to result in potentially serious missing data problems and/or selection bias. So in this study, we explore the potential of using machine learning algorithms trained in data sets that contain information on fetal weight to predict or impute fetal weight in data sets where this information is not available, using a common set of covariates between the two sources. The specific machine learning algorithms that we used were random forests, Bayesian additive regression trees, and generalized boosted models. And we compared these algorithms to standard linear regression and quantile regression. Our analytic strategy is illustrated in Figure 1, where we show how we used two data sets to train our algorithms and then evaluate their performance. So the basic idea was to train our algorithms in part of one data set and then evaluate how well it predicts fetal weight in the second part of the same data set, as well as in an entirely different data set. We evaluated the performance of each algorithm using several techniques, two of which I'll mention here. First, we estimated the median absolute deviation and the mean squared error, comparing the actual and predicted fetal weights in both data sets. We found that Bayesian additive regression trees yielded the lowest overall median absolute deviation. Second, we created a small for gestational age birth variable using our actual data and our predicted data, the predicted fetal weights. And then we checked to see if the confounder adjusted association between smoking and small for gestational age was affected by the algorithm that we used to predict fetal weight. We found that when fetal weight was predicted using standard regression-based methods, this association was underestimated by roughly 50%. However, there was no difference between the actual association between smoking and small for gestational age, that is when we used our actual empirical data, versus when we imputed the fetal weight data using our machine learning algorithms. So overall, this was an exciting project that yielded a trove of interesting findings. Now, while there were some limitations of our approach that should be kept in mind, and which we mention in the paper, we found that machine learning algorithms trained on an external data set holds promise in recovering missing fetal weight information. Thank you.